All right, I'd just like to run through a couple of examples for getting Lewis structures and the Vesper geometries afterwards. This is to kind of run through the procedure that I like to use for getting Lewis structures, especially for those of you that might have had me last semester, just to run through these steps. This method might be a little bit longer for simple molecules. I like it because it works, it always works, and whether it's a very simple molecule or a more complex, more esoteric one, the procedure that you'll go through is exactly the same, and you'll pretty much always get the right answer. So to illustrate most of the points of these things, I'm going to go through actually two examples. One of them is the carbonite ion CO2 2-, and then the other one is going to be sulfur dioxide. So, if you look through my steps to finding optimal Lewis structures, available on the Moodle page, I'm just going to go through these and refer to them by their number. So the first step is, if it's an ionic compound, make sure that you treat the anions and the cations separately. And that's basically because in real life, they don't interchange electrons at all. So you can just treat them as independent entities. So not a problem here. This is an ion, but it's already separated from its cation. So step 2, get the right number of valence electrons for each species. And this is kind of important because if you don't get the right number of valence electrons, you are not going to get the right Lewis structure. So for carbonite, the carbon supplies 4 valence electrons. Each oxygen supplies 6. And then because it's a -2 anion, make sure you add 2 more, giving you a grand total of 18 electrons. For the sulfur dioxide, the sulfur contributes 6. Each of the oxygens contributes 6. So both of these species have 18 valence electrons. Step 3, put together the bonding framework using only single bonds. This is because if it's part of the molecule, then it has to be at least singly bound to one other atom in the molecule. Now, the way that these are written, you can assume that, in this case, the carbon is the central atom and the oxygens are the peripheral ones. So we're going to start, an extra one here, try that again. So carbon atom in the middle, oxygens on the outside. And now I'm going to do them one at a time. So, let's see. Step 3, put 3 non-bonding pairs of electrons around the outside atoms first. So these single bonds already represent 4 of the 18 electrons. So here you would have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, this applies to only non-hydrogen outside atoms. And step 5, if there are any other electrons left over, they have to go on the central atom. In which case, this showed 16 electrons, so we have to have 2 more on the central carbon. All right. So at this point, this is the preliminary structure for this species, and it's probably not correct at this point. The way that you fine-tune it is by looking at either octet compliance or formal charges. And remember that whether you're looking at formal charges or the octet rule, the way you count the shared electrons is different. So I'll start with the octet rule. For octet counting, the electrons are actually shared. So both oxygen atoms have 8 electrons via the octet rule, and the carbon atom actually only has 6. The 2 unshared electrons, and then the 2 coming in from the bond. So that's not perfect. Now, another way to look at this is by formal charge. Now, the difference in the counting there is that the formal charge splits up the shared electrons equally. So by formal charge counting, each of these oxygens in this structure has 7 electrons associated with it. The 6 unshared electrons and 1 from the shared pair. Now remember that the formal charge is equal to the number of valence electrons that element has by itself. minus the number of electrons in that particular species. And if you do it that way, the sign of the charge comes out right. So at this point, both of these oxygens have a -1 formal charge on them. And let's do the same thing for the carbon. So for the carbon, we can count 1, 2, and then 3, 4. Now, carbon usually has 4 valence electrons in it. It has 4 in the structure, which means its formal charge is 0. Now, when you have a polyatomic ion like this, the formal charges need to add up to the overall charge of the species. In this case, -2. If that doesn't work, you've made a mistake somewhere. Now, the idea is that formal charge is not great and you want to minimize it if at all possible. And the way you do that is by redistributing the electrons and going to multiple or higher order bonds. So what you could do, for example, is take one of the unshared pairs on this oxygen and make it a shared pair, giving you this structure right here. Now, has this improved? Both of the oxygens still have 8 electrons by octet counting. The improvement here is that we now have a full octet around the carbon. So that's an improvement. And now let's look at the formal charges. This one hasn't changed, so this oxygen still has a formal charge of -1. Now, this carbon atom now has 5 electrons associated with it by formal charge counting. So it actually has a formal charge of -1 in this structure. This oxygen has 6 electrons associated with it by formal charge counting. The 4 unshared electrons and the 1 shared pair. So that gives it a formal charge of 0. And I would say this structure is better than this because the formal charges haven't gone away, but for a polyatomic ion, you can never completely eliminate them. But you have got a full octet around everything now instead of just 2 of the 3 atoms here. So I would say this is better, which leads us to step 9. And that is if equivalent resonance structures can be drawn, make sure you draw all of them. Now in this case, I arbitrarily chose the right carbon-oxygen bond to be the double bond. There's nothing to say that we couldn't have done it the opposite way. So we would have a structure that looks like this. And this whole thing has a -2 charge. So you've got 2 equivalent resonance structures for this structure, and this is the Lewis structure for carbonite. Now, let's look at our friend sulfate, which is isoelectronic, so it should be very similar. The way it's written, or sulfur dioxide. Start with sulfur in the middle, oxygen on the outside. That is 4 of the 18 electrons. 1, 2, 3, 4, 5. So now we've got 10, 11, 12, 13, 14, 15, 16, 17, and so those are 18 electrons. Again, we had to put 1 on the central atom. Count the formal charges. So by formal charge counting, you have 7 electrons on this oxygen, so it has a formal charge of -1. The other oxygen is the same. The sulfur has 4 electrons associated with it by formal charge counting. Sulfur likes to have 6, which means that has a +2 formal charge. Those add up to 0. It's a neutral molecule, so we actually counted the right number of electrons. Now, where do you go from here? The other problem with this structure is that the Octet Rule is not satisfied for sulfur. It is underfilled at this point. So, do what we normally do and make multiple bonds. So, let's make this one the double bond this time. Alright, so this one is unchanged. Formal charge on that oxygen, still -1. The formal charge on this oxygen is now 0. It has 6 electrons associated with it. The 2 unshared electrons half of that shared, those two shared pairs. So that gives us a formal charge of 0. And for the sulfur, you can attribute 1, 2, 3, 4, 5 electrons. Normally has 6. So the formal charge here is +1. So we've reduced the magnitude on the sulfur, we've taken it off one of the oxygens, and we actually have filled the octet on sulfur. But there's still formal charge on the sulfur and the oxygen. Now remember though that sulfur is a third row element, and when you have a third row or greater element, you can exceed an octet if it makes the formal charge situation better. So what we could do in this case is the same thing again. Take one of the unshared pairs on the oxygen, make it a double bond. The formal charge on this oxygen, there's 1, 2, 3, 4, 5, 6 electrons. It normally has 6 electrons. So it has a formal charge of 0. And the same thing for the sulfur. By formal charge counting, you can assign to it 1, 2, 3, 4, 5, 6 electrons. The octet is now overfilled. By octet counting, that sulfur has 10 electrons, but it's a third row element, you can do that. So this is probably the correct Lewis structure for sulfur dioxide. Now, Vesper, what do these things look like? Both of them have 3 electron domains around the central atom, which means that the electronic geometry, as we called it, is going to be trigonal pyramidal. In both cases, one of the 3 domains is an unshared pair, which means the molecular geometry is going to be different, and it is the shape we simply call bent. So sulfur, the trioxide, for example, actually looks more like this. And the carbonite is also bent as well. So this is just sort of the basic rundown of the way that I like to go do Lewis structures. Again, you can get this handout that's got all the steps explicitly written out and do plenty of examples.